Hey guys, Mrs. Stans here. So today we'll be doing lesson 3. We will be calculating the percent of increase or percent of decrease, and we will see how it applies to our exponential growth and decay functions. You can check your homework answers when you get a chance, and you can start lesson 3's due now, and I will be going over it with you shortly. So hopefully you remember from 6th grade even how to convert percents into decimals, right? The quick, easy trick actually is to just move the decimal point 2 places. So to change 5% into a decimal, we move it 2 places to the left, which would make it a 0.05. Move this one 2 places, 0.025. If we move this one 2 places, it's 0.0045. And this, remember, 2 3/4% is the same thing as 2.75%. Right now I didn't change it to a decimal. I just rewrote this mixed number as a decimal, but they're still both percents. If I want to change the percent to a decimal, I have to move it 2 places to the left, so I get 0.0275. So number 2, agronomists are studying how quickly the population of an invasive species of beetle will increase in a controlled farm setting. They calculate that the population is increasing at a steady rate of 6% per week. At the beginning of the week, the population was 350 beetles. So they want us to find the population of beetles a week later by first finding 6% of 350 and adding it to the original population. Now I know you did percents last year in 7th grade, and I think the focus was really on writing a proportion. Remember, you learned part over whole equals percent over 100. So I could set up a proportion x over 350 equals 6 over 100 and solve that. But the real reason why we had do now number 1 with changing our percents to decimals is because actually we could find the percent of a number by multiplying. So we could change the 6% to a decimal, 0.06, and do 0.06 times 350. So I really want you to change your percents to decimals and then multiply, because that's how we can use it in our exponential functions. So on our calculator, 0.06 times 350 is 21. So remember, this is about the population of beetles increasing. So it means that in the first week it increased by 21 beetles. But the question is, find the population of beetles a week later. So don't forget, we have to add that 21 on. So we had 350 beetles, and then it increased by 21. Therefore, we have 371 beetles at the end of the first week. And this part B is actually the more important part of the question that pertains to exponential functions. So I know you talked about it last year in 7th grade. It probably wasn't a major focus, but we can find a percent of increase or a percent of decrease by actually first adding the percentage on to 100, right? 100% of something stands for all of it, right? If I asked you what's 100% of the beetles and there were 350 beetles, the answer is 350, right? So 100% just represents all of something. If I have a percentage higher than 100%, that means it increased. So our beetles are increasing by 6% each week. So I could say I want to find 106% of the 350. So that's going to make the 350 increase because 106% is greater than 100%. 100% of the beetles is just 350. 106% of the beetles is going to be greater than 350. So I can change this percent to a decimal by moving it two places, and I get 1.06 that I want to multiply by that 350. So what is 1.06 times 350? Notice we get the answer straight away. The answer is 371. So it is the same answer that we did over here, but I did it in a single multiplication instead of multiplying and adding it on, like a single step, I should say. So what will be the beetle population after 2 weeks? Well, let's again do 106%, right? Because each week it increases by 6%. So it's okay that we're on week 2. Still just an increase of 6% from the week before. So the week before would be 100% of the beetles, and it's increasing by 6%. So it's still 106%, but this time it's not of 350. This time it's of 371 because it's a 6% increase on the week before. So if we move this decimal two places, we're doing 1.06 times 371. And it's 393.26. Now that is an exact amount. Will there be 0.26 of a beetle? No, right? Beetles are born whole. So the beetle population, we could say, is about 393. When we're talking about populations, we tend to talk about it in whole numbers, not in decimals. So these next three problems just practice what we just did. Some of our answers will have decimals. Let's not round it because it's not a real world application. So let's put the exact mathematical answer. So if we're going to increase 440 by 12%, remember an increase of 12% means it's 100% plus 12%, which is 112%, which as a decimal is 1.12. This step here is a mandatory step in my class. Maybe there's some other teachers that wouldn't require it. I need you to do this for me. I need you to show me that you start with 100% and then you add on 12%, you get 112%, and you change it to a decimal. Then you're going to write down what it is that you're putting into your calculator. So 1.12 times 440. Right? All the time when it's not multiple choice, you must show your work. And some students say, well, I just did it on my calculator. Yeah, well, I need to know what you typed into your calculator. So make sure you're always showing your work. So you can see I get 492.8. Letter B, it's an increase of 8%. So 100% plus 8% equals 108%. Move the decimal, 1.08 times 68. and use your calculator. I get 73.44. And letter C, it's increasing by 3.5%, so 100%, plus 3.5% equals 103.5%. Move the decimal twice, 1.035 gets multiplied by 120. And I get 124.2. So this just summarizes what we just did over here with our growth, that you have 100% and then you add on the given percent and then we change it to a decimal. Well, guess what? We could do the same thing with decay. You start with 100% because 100% is all of something. But if it's decaying, now notice it's subtraction. So it's 100% minus the percent they give you. You change it to a decimal and you do your multiplication. So we're going to find the growth or decay rate for each of the situations below, and then we're going to state what the exponential base is. So when I ask you what is the exponential base, I'm really talking about this decimal here. When we did the 100% plus the percent and changed it to a decimal, that's going to be our exponential base. That's going to be our multiplying factor that we talked about in lesson 1. Since this is greater than 1, it's a growth. So here on number 1, a car depreciates, so that's going down at a rate of 12%. So we do 100%, take away 12% to get 88%, change it to a decimal, and you get 0.88. This is the exponential base. So that's why it's so important for me, for you to show the 100% add-on or the 100% subtract away, because it depends on this word that they give you, whether you're adding it or subtracting it. So number 2, a population increases. So that's 100% plus 32%, which is 132%. Change it to a decimal, 1.32. So I want you to try the rest of these up to number 6 and then check your answers with me. You could hit pause. So here's what I got for my answers. I would say that number 5 and 6 were the trickier of the two because it didn't tell you the exact percentage. You had to read the words and decide what the percentage would be. Like in number 5, if half of the tournament's participants are being eliminated, that's 50% of them are being eliminated, right? So also something that stands out to me is a half is the same thing as 0.5. So I can actually go from this word straight to that decimal. Same with number 6. Doubles would mean times by 2. My answer is 2. But why is it 2 according to percentages? Well, you start with 100% of something. If you're doubling it, that means you're getting another 100%, which is 200%, which changed to a decimal is 2. But again, I'd be okay with number 6 if you just took the word doubles and right away knew that the answer was 2. So in lesson 1, we talked about our exponential growth and decay, that A is your y-intercept, and B we called the multiplying factor. It is a base, of course. Sometimes it's a growth factor, sometimes it's a decay factor. Remember, we even said when does it grow and when does it decay. So when the base is greater than 1, it's a growth rate, not decay. And if it's between 0 and 1, then it's a decay. So this talks about being greater than 1, right? If we add something onto 1, that grows. This is a way of showing how it's a decay because it will be between 0 and 1 if I'm taking away the rate from 1. Some people use these formulas when they're writing their exponential growth and decay. I actually kind of use my common sense instead of go to these formulas. I do it the way that I showed you in the beginning of this lesson, even with writing 100% minus or add on the percent depending on whether it's growing or decaying. So let's look at example 1. So Dylan invested $600 in a savings account at a rate of 1.6% annual interest rate. So annual interest rate means that it is growing annually, meaning each year. So I'm going to take this number and do 100% plus 1.6% to get 101.6%, change it to a decimal, 1.016. And I need to use this now in a function. We are going to be writing like a function now. So Dylan invested $600 in a savings account. Well, the amount of money he starts with is actually the y-intercept. So that means I could say that y equals, right? I want to write it as a function, so I start with y equals, or f of x equals, the y-intercept, which is 600, times the base, which is 1.016, and that gets raised to the x power. Now, if I wanted to answer this question, they're asked us to find to the nearest cent the balance in the account after 2 years. 2 is my input, so it goes in place of x. So y equals 600 times 1.016 to the second power. And we can use our calculator for that. Right here on the home screen, we could do 600, then in parentheses, 1.016, close parentheses, raised to the second power. Remember, it did say find to the nearest cent because you see that there are 4 decimal places after the decimal point. Money isn't that way. Money only has 2 decimal places, so we do have to round this. So it would be $619.35. $619.35. So this is like what we're in for the remainder of the unit, taking a word problem and writing it as an equation, which is a function, and possibly finding an output given a certain input. Let's take a look at number 2. This is decay. Jess bought a minivan in 2011 for $25,900. The car depreciates. That means it's losing value. So let's write our 100% minus 6.5% to get 93.5%. Change it to a decimal, 0.935. And then it says write an equation to represent the value of the car A. Let's make sure we use now the variables that they want us to after t years. So A is like the name of the function. And the initial cost of the minivan was $25,900. My base is the 0.935. It is depreciating or decaying, and that's why it's a number between 0 and 1. And we have to raise it to the t power. We're using a t because that's what they told us to use for years. So your exponent does always represent time when we're talking about real world situations. And a lot of times we like to use the letter t for time. I could write a of t instead of just a. Either way would be acceptable. And we want to determine the value of the car to the nearest dollar in 2017. So how many years has passed then? If you said 6, you're right. So in place of my t, I'll put a 6 and use my calculator. And we have to determine to the nearest dollar. So that means no cents. So that would be 17,305, right? If I'm rounding, 17,305. That's how much it's worth after 6 years. The king purchases a house for $363,000 and it appreciates. That means it's increasing at 2.5%. So let's do 100% plus 2.5% to get 102.5%. As a decimal, that's 1.025. So if we write our exponential equation, do they tell us what to call it? I don't see it. So I'll call it y equals the initial cost times that base to the t power. And then we want to know what it's worth in 15 years, so we replace the t with a 15. And this is what I get for my answer for the worth of the house. Next, during the past several years, the population of Feldsville County, New York has been decreasing at an average rate of 0.3% per year. 100% minus 0.3%, that really is just 99.7%, right? It only decreased by 0.3%. Change this to a decimal, 0.997. In 2000, its population was 88,647. So that's our starting amount. Multiply it by the base. And I'll use a t for time. They want us to find out how many people lived in Feldsville County in 2012. So how many years has passed? It's been 12 years. Put a 12 in place of the t and find your answer. And I love these two last questions. They're just checking to make sure you understand what the percent of increase or decrease is when they give you the function. So they're talking about the value of a car depreciates according to this function. P is the purchase price, T is the time, and they want us to state the percent that the value of the car decreases by. It's definitely a decrease because this is less than 1. And where does that 0.88 come from? Well, that 0.88 really is 88%, but that's not the percent that the car decreases. Remember that 88% came from some subtraction. It was 100% minus 12%. That gave me the 88%. So it depreciates by 12%. So keep in mind that the percent that you see in the problem is not the percent that it's increasing or decreasing, because that comes from some sort of addition or subtraction. So number 6, this function, I already know that it's a growth, right? It's greater than 1. So it represents, in dollars, an antique toy collection T years after its purchase. And what's the rate of appreciation? Well, this 1.018 is really 101.8%, which comes from 100% plus 1.8%. So it appreciates by 1.8%. And that's it. Your homework's the next page. I'll see you soon. Bye.